Okay, this is 1.3, making use of energy. This is lesson 5. But just before this page, you got a question. Thermal conduction. This is where heat energy is moved or transferred through a solid. Conduction occurs less well in liquids and hardly at all in gases. Why is that? Well, the distances between particles in a liquid are greater, and in a gas they are even further. So if you imagine in a gas, the particles are so far apart that if one starts to vibrate as a result of being heated up, it won't hit an adjacent particle. There aren't any particles close to it. So let us move on to this paragraph now on thermal conduction. Number 1, you heat up one end of an object. Number 1. Number 2, the particle starts to wobble or vibrate more. Number 3, the particles bang into or collide with adjacent particles. Adjacent means next door neighbour particles. And then number 4, energy is transferred from the hot end of the object to the colder end of the object. The heat stroke thermal energy within an object is the total amount of kinetic energy contained within its particles. Okay, why are metals such excellent conductors of electricity? Well, the first reason is the particles are very close together. They're in a sort of uniform shape. So if one starts to vibrate, the next one will. But also, we have got these small little electrons, and they're represented by the small dots here. Now, in a metal, those electrons orbit around the outside of the metal ion, but they can also move. They are free to move between ions. So that means that there is going to be more collisions, more vibrations, and more heat being transferred through. This is why metals are such good conductors. Much better than non-metals. You have a read through this passage and colour or underline the correct answer. I've effectively done it for you. Question 1 is in green, the answer is in green. Next part. Does the amount of insulation around a cup of tea reduce its rate of heat loss? Well, of course it will. The teacup with 2 foam layers around it is going to lose heat over a much longer period than the one without any insulation at all. So the independent variable here is the number of layers of foam insulation. Does not have any units. The dependent variable here will be the temperature of the tea over whatever the time period is, and it's over 90 minutes. And then our 3 control variables. What could we make sure that we keep the same to make sure that we've got a fair test? Well, number 1, the volume of the liquid, the type of liquid, the starting temperature of the liquid, what the teacup is made out of, the rate of stirring, and what the lid is made of as well. So the room temperature, all of those are control variables. And finally, for this lesson, we're going to look at the time over which the water or tea temperature drops within those 3 teacups. And number 1 was label up the axes. Each large square for time is 10 minutes. done that, labelled it up, and each large square is 10 minutes. And then each large square vertically represents a water temperature of 20 degrees. So number 1 is done. Then it says, question 1, what was the starting temperature of the liquid? The starting temperature of the liquid is up here, and I would estimate that to be either 97 or 98 degrees centigrade. Number 2, show extraction lines and calculate the temperature at 32. So you get your ruler, you put it at 32 minutes, which is just about here. And then you move it round like so, and you get this value here. And with the extraction lines, what was the temperature at 32 minutes? That would have been 44 degrees C. Is lovely. So 44 degrees C was your answer to question 2. Question 3, show the extraction lines and calculate the time when the liquid was 74 degrees C. Let's try that now. There's 74. Turn the ruler around, show your extraction lines. Whoops. Okay, my extraction line there should be 8 minutes. So 8 minutes for question 3. Question 4, at what time did the liquid reach room temperature, and what was that temperature? That would be this value here. So that reached the room temperature after 45 minutes. I really should be putting extraction lines in. And that temperature, if I move across, would be 30, 32, 34, 36 degrees C. So question 4, 45 minutes, and the room temperature was a very high 36 degrees C. Question 5, use colours to draw in lines for no foam. No foam, the value will drop very quickly. It will hit 36 degrees and then it won't go below that. So there is my value there for the no foam. Two foam, this purple line, the rate at which it loses heat will be much slower than the one foam, the blue line, but eventually it'll hit 36 degrees and then just carry on. That is your answer to question 5. What is your conclusion for the experiment? As you increase the number of foam layers, the rate at which the water temperature decreases actually decreases. And finally, an extension question. Where did the largest rate of temperature decrease occur, and why did this occur? It always occurred up here. And that is because the largest rate of temperature decrease occurred at the start of the experiment, I'd say within the first 10 minutes, and that is because you have got the biggest difference between the actual temperature of the water in the cup of tea and room temperature. There'll be the biggest difference then. You know, it started at 98 degrees C and the room temperature was only 36 degrees C. So that is why you had the largest rate of temperature decrease.